Welcome to the Explainer. Now, for this final module, protection and shielding, we are going to completely shift our mindset. We're taking a concept that usually generates a lot of vague fear and transforming it into an empowered, engineering-level understanding. Seriously, by the time we're done today, you're going to see exactly how we manage and tame one of nature's most fascinating forces.
You know, there's a truth we really need to confront right out of the gate. As our source material perfectly captures, there is a word that stops conversations at dinner parties. That word is radiation. It's one of those words that makes people's eyes widen and their voices drop. And let's be honest, almost everything most people believe about it is either wrong, exaggerated, or just completely missing the crucial context. But here is the reality. Radiation is not some modern, unnatural invention. It's definitely not just a byproduct of the nuclear age. It has literally been around since the universe began.
In fact, think about the everyday world around us. I'm talking directly to you right now. You are actually being irradiated as we speak, by the ground beneath your feet, by the building materials surrounding you, by cosmic rays from space, and even by the food you eat. There's an isotope called potassium-40 that is literally decaying inside your own muscles as you listen to this explainer. It's just a completely natural, unavoidable part of our physical world. And once we accept that, we can figure out exactly how to manage it.
Okay, let's dive into our roadmap for today. We'll start with the reality of radiation, look at how we measure the invisible hazard, introduce the ALARA protection principle, explore designing nuclear shielding systems, and finally, wrap up with detecting and verifying safety.
All right, starting off with Section 1, the reality of radiation. Before we can build a shield, we have to define the exact physical variables we're dealing with. Now, what's really interesting here is that not all radiation is created equal, and how it interacts with matter dictates exactly how we stop it. For example, alpha radiation is heavy and highly charged. It loses energy so fast that a single piece of paper or just the dead layer of your skin completely stops it. It's really only a hazard if inhaled or ingested. Beta particles, they travel a bit further but can easily be stopped by plastic or aluminum. And a fun fact, you actually don't want to use lead for beta because the rapid deceleration creates secondary X-rays. Gamma, on the other hand, carries no charge or mass and is highly penetrating. So for that, we need heavy materials like lead or concrete. And neutrons, well, they're uncharged and interact directly with nuclei, so dense lead is pretty much useless there. You need hydrogen-rich materials like water or polyethylene to slow them down.
So, understanding the types is step 1, which brings us to Section 2, measuring the invisible hazard. Because you literally can't engineer a shield if you can't quantify the threat, right?
Okay, there is a super crucial distinction here that confuses a lot of people, the gray versus the sievert. The absorbed dose, which is measured in grays, is just raw physics. It tells us the sheer amount of energy deposited per unit mass of material, literally 1 joule per kilogram. But here's the thing, human bodies aren't just solid blocks of material. The effective dose, measured in sieverts, accounts for our biological reality. For instance, because alpha particles cause really intense complex DNA damage, an alpha dose inside the body is multiplied by a weighting factor of 20 compared to gamma rays. The sievert is the number that tells us the actual biological risk we need to design our shielding against.
Moving on to Section 3, the ALARA protection principle. Now that we know what we're measuring, how do we actually protect against it?
ALARA stands for as low as reasonably achievable, and it is the absolute ultimate strategy for radiation protection. In the real world, engineers and radiation workers use 3 basic physical controls to achieve this. First up is time. You simply minimize how long you are near a source. Second is distance. This one is incredibly powerful because it exploits the inverse square law. If you just double your distance from a point source of radiation, your dose rate drops to 1/4. It's basically mathematical magic. And third, when time and distance just aren't enough, we deploy shielding, putting physical engineering barriers between us and the source.
And that leads us beautifully into Section 4, designing nuclear shielding systems. Let's look at how we actually build these incredible barriers.
Since gamma radiation is our primary external hazard, we have to understand its behavior. It interacts with matter in 3 distinct ways. At low energies, the photoelectric effect completely absorbs it, which is exactly why lead is your best friend here. But if you bump up the energy, Compton scattering bounces the gamma ray around, meaning we just need bulk mass, like incredibly thick concrete, to scatter and absorb it. And at the absolute highest energies, pair production actually creates an electron-positron pair. So, our material choices are entirely 100% dictated by these 3 quantum behaviors.
So the really crucial point to grasp here is that radiation attenuation is exponential. You can never reduce gamma radiation to absolute zero with a finite wall, but you can predictably cut it in half over and over again using something called the half-value layer, or HVL. If one HVL thickness cuts the radiation to 50%, 2 layers cut it to 25%, 3 layers get you down to 12.5%, and so on. It is a brilliant, immediately practical concept for shielding design.
Now, when we apply this math to the real world, the scale is just staggering. 10 billion, a reduction factor of 10 to the 10. Reactor shielding doesn't just use 1 or 2 half-value layers. It typically uses tens of them. By stacking these layers, say with 2 to 3 meters of dense concrete, engineers achieve massive reduction factors. They are mathematically guaranteeing that the radiation outside the biological shield drops by a factor of 10 billion or more, compared to what's inside the reactor core.
Let's move on and see how these concepts build an actual real-world fortress. A nuclear power plant is basically designed as a series of concentric medieval-style barriers. First, the fuel cladding holds the radioactive material tightly. Second, the heavy steel of the primary coolant pipework traps anything that manages to escape. Third, you have that massive concrete biological shield we just talked about. And finally, the reactor building itself. Each single layer successively reduces the hazard.
We actually see this most dramatically with spent nuclear fuel. Freshly discharged fuel assemblies are so intensely radioactive that direct exposure to them would literally be fatal in minutes. But simply by placing that assembly under 8 to 10 meters of water in a spent fuel pool, it is rendered completely 100% harmless to anyone above it. The water serves as both a perfect biological shield and a coolant. A worker can literally stand right at the edge of the pool, directly above a deadly assembly, and safely go about their day. That is pure physics at work.
Finally, Section 5, detecting and verifying safety. Because let's be real, all this engineering means absolutely nothing if we can't prove it actually works. You cannot protect against what you cannot measure. To verify our safety in real time, we use a really robust toolkit. For simple contamination, Geiger-Miller tubes are your classic, reliable choice. Need to identify exact energies? Well, scintillation detectors emit light to show us precisely what we're looking at. Add in highly accurate ionization chambers and electronic personal dosimeters tracking real-time exposure for the workers themselves, and you have a system that constantly proves our shielding math works. This is exactly why the nuclear industry maintains one of the best occupational safety records in the whole world.
Which brings us to our final thought. As we've seen throughout this explainer, radiation isn't magic, and it really shouldn't be a source of vague, paralyzing fear. It is a strictly manageable physical phenomenon. We know the sources, we understand the quantum physics of how to block it, and we have the exact math to measure it. So I'll leave you with this question. Is it time we let the engineering outweigh the fear? Think about it. Thanks for joining me today, and keep exploring.